Okay, let's get started. So we were working on this problem last time. There is a U-shaped conducting rail, and it's in a magnetic field, and the magnetic field is pointing into the page or into the screen, and you have a conducting bar which is moving, which is being pulled to the right at 2 centimeters per second, and as a consequence you will have some motional EMF. We saw last time that when you pull a bar in magnetic field, you will have some positive charge on one side and negative charge on the other side, okay, depending on which way you are moving the rod. And if it is connected to some wire, then it will act as a battery. So if you connect a light bulb, then you will see the light bulb will lit because of the charge. So this question is asking how much current will flow in this wire because of this motional EMF. So you will have some delta V, or it's also denoted by this E, same thing, motional EMF, and because of that you will have some current I, and we want to find what that I is, which we call induced current. And last time we derived this relationship for motional EMF. Motional EMF is given by that was VLB, I think. So that's the motional EMF, and we want to find I induced, and Ohm's law tells us delta V is I times R. So then that means we want to find I would be delta V over R. So delta V would be EMF over R. So EMF is VLB over R. So V is the speed of the rod, L is the length of the rod, B is the magnetic field, and R is the resistance of this circuit. Okay. So speed 2 centimeters, 2 times 10 to negative 2 meter per second. L is the length of the rod, which is 10 centimeters, 10 times 10 to negative 2, or 0.1. Magnetic field 2.2 Tesla, and R is the resistance 1.2 ohms. And if you do that, you get an answer. Can you guys do the calculation and tell me the answer? 3.7 times 10 to negative 3 amperes. That's the I induced. Okay, I induced. Now part B, that's A. What force is needed to keep it moving with this speed? Now we know that when a conductor or a wire carrying some current is moved in some magnetic field, it will feel some force. So let's say you have a piece of wire, and the piece of wire is carrying some current. So this will feel some force. Okay. In this case, if you use the right hand rule, the force would be in this direction. Okay. Because current is going that way and magnetic field is into the page. So you point your fingers towards the current is going that way, and then curl towards the magnetic field. So magnetic field is into the page. So magnetic field is into the page, current is going up, so curl towards the magnetic field, thumb is pointing to the left. Okay, so the force is to the left. So this conductor will feel some force to the left. If you want to move this conductor at a constant speed, then you will need to exert same amount of force as this force, because this acts as a resistance. Okay, so it will tend to slow down this metal bar. So to keep this moving at constant speed, you need same amount of force on this side, and we want to find that force. Okay, what is that force that will keep the object or the metal bar in constant motion? So how do we find that force? We already know the formula for force felt by a conductor or a wire carrying some current. Do you guys remember the formula for the force felt by a wire in a magnetic field? Yes, ILB sine theta. This theta is angle between I and B. In this case, I is up, B is into the page. So I is up, B is into the page. That means it's 90 degrees. So theta is 90 degrees. So that's 90 degrees, which is 1. Okay, F is I is induced current, which is that value, but I will first use this expression. Okay, I will not plug in the numbers. You can do that. Okay, that's not problem, but I want to show you the expression first before I plug in the numbers. But if you like, again, you can just plug in the number. So I is that. I'm going to plug that expression here. So VLB over R. Okay, we have L and B. Sine theta is 1. So let's simplify this. V, L and L is L squared, B and B is B squared over R. Okay, and you can plug all the values here. So V is 2 centimeters per second, 2 times 10 to negative 2 meters per second. L is the length, which is 10 centimeters. Is that right? 10 centimeters. B is 2.2. 10 times negative 2 meter squared. B is 2.2 Tesla squared. And the resistance, what was the resistance? 1.2 ohms. So let's do the calculation and see what you get. .14 times 10 to negative 4 Newton, and this is to the left. So this is the force on the conductor carrying current.
Why is to the left again?
Using the right hand rule. So the current is going up and magnetic field is pointing into the page. So point your fingers towards I and curl towards B. Okay, up and then curl inward. Thumb is pointing to the left. Now to keep the conductor moving at constant speed, you need to cancel that force, okay, which you can do by applying the same force in the opposite direction. You need to apply F is equal to 8.14, same force, but in opposite direction. Okay, that's number 2. Let's look at number 3. What is the mechanical power required to maintain this speed? So now we need to find the power. So basically, applying force means you are applying some power. Okay. What's the definition of power? This is from physics 1. Force times distance is work. It is related to work. I can say that it is these two are related. Some V times I is, it's not mechanical, it's electrical. So there are two types of power. They are more or less same. One is mechanical power. If you are using your hand or machine, it's mechanical power, okay, which is physics 1. And there is also electric power, which is physics 2. So power is also I times delta V. But we are talking about the mechanical power, not electric power. This is also right, but we want mechanical power. So what's the mechanical power? You don't have done this in physics 1. Maybe you forgot. Power. Delta KE. That's also work, yeah. So that's work energy theorem. Power is how fast you can do a work, okay, the rate at which you do the work. Whenever you see the word rate, it has to do with the time, right? So how fast you do the work over time. And we know work is force times distance. So work over time, work is force times distance over time. So force times distance over time. Okay, I'm just rearranging the things here. Force is that, and then distance over time. And distance over time is speed, constant speed. So power is F times V. Okay, this is very useful formula. So that means we want to use force times speed to find P. And we already have the expression for force. If you want, you can use this formula directly and then plug the speed. Okay, you can do that. But I'm going to write an expression first, which you don't need to do actually, but I want to show the expression. So the expression for force is that VL squared B squared over R. VL squared B squared over R. That's the expression for force. And I have V here. So then power would be V squared L squared B squared over R. Okay, that's the expression for power. And this is mechanical power. So plug in the numbers. So you can do directly or plug the numbers in this one, whichever way you want. We already found F, 8.14 times 10 to negative 4. V is that 2.0? So that will give you the power. Or if you like, you can also plug in the numbers in this expression. That will also give you the same thing, because these two are the same expressions. So that will give me 16 1.28 1.6 times 10 to negative 5 maybe. (1.6 times 10 to negative 5). The unit of power is watt. Now the third one is the electric power. Okay, it's asking at what rate the energy is generated. So rate at which energy is generated is also power. Power is energy over time, which is also work. Okay, energy and work are more or less same thing, because you need energy to do the work. If you do work, the work is stored in form of energy. So work and energy are same thing. So whenever we talk about this energy here, this is about the electrical energy. So electrical energy generated per unit time is electric power, and we know electric power is given by I times V, and in this case you can say I times E, because we are talking about electromotive force. If you want, you can also write I times V. Okay, same thing. Okay, we know I, we know R, so we want to write Ohm's law to write V in terms of I and R. So V is I R, use that here. V is I times R. I and I is I squared. Okay, now you can substitute your I and R here, but I will do one more thing. Okay, you can do the plug in the numbers here and get the answer, but I want to show you one more thing here. Okay, that's not necessary, but just for the verification of something. So we have I. What's the expression for I that we got? Okay, tell me, you guys tell me what the expression we got for I. No, not that one. The I we got in the part A. Not the value, the expression. Okay, you can do use the value here, but I want to show you an expression. VBL over R. Okay, that's what I was looking for. So that's I, and that's squared. Okay, R. So V is V squared, B squared, L squared, R squared. Okay, that's squaring everything, and then square this one will cancel. So V squared, B squared, L squared over R. This is electric power. This is mechanical power. What do you see here? Exactly same. So whatever power you input on that bar or on that system, the same power will be converted into electric form. So the power you use is converted to electrical power. That's the conservation of energy. Okay, this is just to show that mechanical power is converted to electric power. Conservation of energy. The power you use has to go somewhere. It cannot just dissipate, and it is converted to electric power. And you don't need to show that. Okay, you can stop at this point. You can just find a value here. This is just to show you the conservation of energy. So let me write a value here. So what you got for I square r? Let's plug in the number here and get the value. Now you tell me what is I. So, Caitlin, what is I? 3.7 times 10 to the negative 3. That seems really, really. You still need to square that?
Okay, that value is 0.0074.
With square?
With square.
0.0074 amperes. Okay, and R is 1.2 ohms. When you do that, what you get?
You should get the same answer as our first one.
Okay, that's good. That's good. So you get 1.6 times 10 to the negative 5.
Yes.
It's not 0.0074.
No, it's not.
1.4.
So you got 1.4.
When I did it, I just plugged in the square into the function.
Okay.
To do it individually.
Okay. So this is negative 4. Okay. So you get the same answer here as in this part, which is again because of the conservation of energy. I think that completes number 1. Any question on number 1? Okay, so let's look at number 2. So number 2 is basically finding the flux through some area. Okay. So we know that magnetic field has some direction. Okay, so this is magnetic field. It's going, let's say, to the board, and let's say this is a loop. Okay, some kind of loop, and this loop has some area. Let's consider some form of loop. It could be a circular, semicircular, or a square, or any kind of loop. Okay, loop means it's a loop of wire, metal wire. So this loop has some area, and this loop is in some magnetic field. So magnetic field is going through that loop. Okay, so we have magnetic field going through the loop, going into the surface, going through the surface of the loop. This area also has some direction. Okay, not just the magnetic field, the area also has some direction. So the direction of the magnetic the area is perpendicular to its face. So this is the face of the loop, and its direction is perpendicular to that face. So this is the direction of that area. So this has some area, and that's the direction of the area. Okay, so that's why we also call this as area vector. Okay, area vector has a value which is the area, and it also has the direction. Direction is perpendicular to the plane or the surface. Okay. Direction is perpendicular to the surface. So flux, magnetic flux in this case, is defined as, it's the product of magnetic field, area, and cosine of angle between B and A. Okay, it is denoted by Greek letter phi. So it also tells us that how much magnetic field is passing through some area. So the magnetic flux depends not only on B and A, it also depends on theta, angle theta. How? So let me see if I have a loop. So let's consider that the magnetic field is going that way, okay, to the right. I can denote the magnetic field with a bunch of lines. So if I orient my loop like this, the area has the direction in the same direction as this B. So B is pointing to the right, and my area is also pointing in the same direction. That's my area. Okay? Again, area is perpendicular to the face. When these two are parallel, there is a maximum number of lines passing through the surface. Okay? So phi is maximum. Now when I orient this in different way, okay, now I change the angle between B and A. There's less number of lines passing through this. Okay, so it's missing this bottom line and the top line. If I further change the angle, less number of lines, 0 line. Okay, so when I orient like this, there is no magnetic lines going through the face. It's going that way, so there is no going through the face. So when this B is perpendicular to the area, flux is 0. So flux depends on how you orient the loop. Okay, if you orient like this, there's maximum flux. If you orient like this, there is 0 flux. So that's what the question is. What is the flux when the angle between the vector is, first part is, what are the maximum and minimum flux? Okay. So for maximum flux, this angle would be, now you guys tell me what should be the angle for the maximum flux between B and A to get the maximum flux. 90? That's the direction of A. They are parallel, right? B and A are parallel. Parallel means what's the angle? 0 degrees, right? You can also say 180, it would be just the difference of minus sign. So whenever they are parallel, is 0 degrees. Okay, do not be confused with the area vector. Area vector is always perpendicular to the face. Okay, that's the area vector. So they are in the same direction. That means its angle between B and A is 0 degrees. So B is 1.23 Tesla. Area of the loop, in this case it's a circular loop. Okay, I didn't draw this correctly. I was just drawing some generic loop, but the question is about the circular loop. For a circular loop, area is pi r squared, right? So pi, radius is 0.0 squared. So that will give us the maximum flux. So let's find that out. Let's do the calculation. Sorry, 20. 0.1? 0.16. Okay. So what's the unit of Tesla? I mean, what's the unit of magnetic flux? You guys can guess that by looking at these quantities. Exactly, yes. So Tesla meter squared. So that's the maximum. Now let's look at the minimum. You should know minimum. We don't even need to calculate the minimum. You guys can tell what the minimum flux is. So minimum flux is when you see here, when it's perpendicular like that. No flux at all. Okay. So BA cosine when B and A are 90 degrees, and cosine of 90 degrees is 0. Okay, so you don't even need to calculate. So it's just 0. Okay. Now the third part is asking to find the flux when the angle between V and B is 45 degrees. When you're orienting like this. Okay. So this is the area. This is the area vector, okay? And the area vector and magnetic field is actually, it should be like this, sorry. This is the area vector, and the magnetic field and area vector are 45 degrees. So that's the magnetic field, and that's the front view of the loop, and area vector is perpendicular to that. This angle is 45 degrees. So BA cosine theta, B is 1.2 Tesla, A is pi r squared, and then cosine 45 degrees. You already have this value, so you can just multiply this value by 45 cosine 45 degrees. So 0.16 times cosine 45 degrees, which would be about 1 maybe. No, cosine 45 1 over root. So 0.11, okay, 0.11 Tesla meter squared. Okay. So that's the magnetic flux. Again, magnetic flux tells us how much magnetic field is passing through some loop like this. Okay, the loop could be circular, rectangular, semicircular, any kind of shape. So now we want to find the induced current in a loop. Okay, let's say you have some magnetic field like that, and then you have a loop like this. So initially there is no magnetic field. Okay, magnetic field is 0, and in 15 millisecond time you switch on the magnetic field of 0.55 Tesla. As a result, you produce some current in this. So what's the current? The main idea here is to do this problem, you need the concept called Faraday's law. Let's just get rid of that. So Faraday found when there is change in flux, EMF or current is induced or produced. Okay, that's the fundamental principle behind which we are getting all the current. So in order to get the current or induced EMF, you need to change the flux. And Faraday's law tells us that the EMF that you get by changing the flux is given by minus n and rate of change of flux. Okay, so this is what you need to get the EMF. So this n is the number of turns in the loop. Okay, you have a loop like this. How many turns you have? That's the n. For example, in this case, I have 1 turn, so n is 1. You can have more number of loops for other cases. And we know that in this case, phi is defined as BA cosine theta. So we want to get E. To get E, we will change phi. Now, how many ways we can change phi? Our main purpose here is to change phi to get E. Okay, so how many ways you can change phi? E is number of loops times delta. Phi is BA cosine theta over delta t. Okay, I'm just plugging this in this equation, the definition of flux. So to change the flux, we can either change B or A or theta. So there are 3 ways we can change the flux. Okay, so flux can be changed, and why we want to change the flux? We want to change the flux to get that, okay, EMF or current. So flux can be changed by changing either magnetic field, area, or orientation of the loop. So if I change the magnetic field, what will be the EMF? So we have minus n. I'm changing just the magnetic field. Okay, I'm not changing A and cosine theta. That means these two are constant for this case. So I can pull this out of the parenthesis. So I can pull A out, I can pull cosine theta out, and I'm changing B, okay, with time. So that's when I'm changing B. Now when I'm changing area, look at this formula. We have EMF given by n. I am changing A, but I'm keeping B and cosine theta constant. So pull B out, it's constant, and cosine theta also constant, pull it out. So then I will have delta A over delta T, because that's what I'm changing. In the third case, I am keeping B and A constant, but I'm changing cosine or theta. So pull B out, A out, because they are constant. I'm changing delta, I'm changing cosine theta. So you can produce electricity, which means current or EMF, by doing three things. Okay, by either changing the magnetic field, or by changing the area of the loop in the magnetic field, or by changing the orientation. Okay, if you do one of these three things, you will produce current. And that's how we get the current for our everyday use. Now let's look at each of the conditions, each of the cases. So look at the first problem, the third problem. So which one is this one? Out of these three, let's get rid of that. So decide which one is this one. Are we changing B? Are we changing A? Are we changing theta? Initially magnetic field is, sorry, theta. So we have a circular coil, and the circular coil is between the poles of an electromagnet like this. Okay, so in the U-shaped electromagnetic, no, let's not write that. So it's between the poles of the magnets. So we have north pole, we have south pole. So we have two poles of magnet, and there is this loop, and magnetic field is going through that loop. Okay, and we are not changing the area. Area is constant. It doesn't say area is changing, and we are also not changing the orientation. It says it's just inserted between the electromagnet magnet poles. Okay, just like that. It doesn't say the orientation, but we assume that it's like that. Okay, we assume that area is that way and magnetic field is also that way, same direction. So there is no change in orientation or area. What we are changing is, see here, initially at t equal to 0, magnetic field is 0, but in 15 milliseconds, in delta t of 15 milliseconds, we change the magnetic field to 15 milliseconds. Sorry, magnetic field to 0.55 Tesla. So that means delta B over delta T is, delta B is 0.55 Tesla final minus initially is 0, and time duration is 15 milliseconds. So that's what we are changing. Okay, we are changing the magnetic field with time. So we want to find the induced current. So to find the induced current, we first find E. E is Faraday's law is N delta phi over delta T. There is also minus sign here, but to find the value or magnitude, we don't need to worry about minus sign. Minus sign basically tells us the direction. We'll talk about the direction in the next part, next class. So we have a minus here. Let's neglect the minus. So how many turns we have? 10. Okay. And what is phi? Phi is B A cosine theta. We are not changing A, we are not changing that, we are not changing that, so we can pull that out. So 10 times A cosine theta. We are changing only B, so B, leave it in delta. So 10, area of the loop is pi r squared. We are given the circumference. Okay, circumference is 2 pi r. We are given that 2 pi r is 20 centimeters. You can find r. R is 20 centimeters over 2 pi. So that's 10 over pi centimeters is the radius. Okay, so area is 10 over pi. Area is pi r squared. So that's pi r squared. So pi r is 10 pi squared. Okay, changing that to meter is 10 to negative 2. That's the area. And then cosine. What's the angle between A and B? What's the area? What's the angle? 0. Yes, they are parallel. So that's 0 degrees. And then delta B over delta T is whatever you get from here. So that's 0.55 Tesla over 15 times 10 to negative 3. Okay, so when you do that calculation, that will give you EMF. So let's find that out. So if you guys have a number, please give me a number. 0.17 volts. 0.1.
1.17.
Oh, okay. 1.17. Sorry. So that's the EMF, and then we want to find the induced current, and Ohm's law tells us delta V is IR, and I is delta V over R, and delta V is EMF. So EMF over R, it gives induced current. So 1.17 over resistance. Resistance of the loop 1.12 ohms, and that will give us the induced current. Okay, that's what number 3 is. Okay, I think that's all for this lecture. We'll continue this in the next one. The next one would be on some online platform.
No class Wednesday.
Huh?
The school dismissed Wednesday.
Wednesday is Thanksgiving break, right? Do we have class on Wednesday?
Oh, it's Thursday, Friday.
I think we have Thanksgiving break starting from Wednesday. Yeah. So next class will be online after Thanksgiving. So have a great Thanksgiving break. We'll see online after Thanksgiving.
How does that work for finals?